Hello, everyone. My name is Mariam Al-Hawaj. I'm a teaching fellow at Trinity College, Dublin. Today, I want to talk about generalized pseudo-Anosov maps arising from Hubbard trees. So the work is trying to connect the two areas of complex dynamics and geometric topology or geometric group theory. In the complex dynamics, we have the Mandelbrot set related to the quadratic polynomial on the complex plane. For each parameter here, there's a nice picture of Julia set. I'll define these soon. And for each Julia set, there is inside it a Hubbard tree. And in the geometric topology or geometric group theory, we are working on surfaces and foliations and pseudo-Anosov maps. And I'm trying to see, starting with the Hubbard tree from complex dynamics, can I construct a generalized pseudo-Anosov in the geometric topology or geometric group theory? So this is the question. Can a complex dynamics object like Hubbard tree be extended to a geometric group theory object like generalized pseudo-Anosov? So I will need some background. Let's start with complex dynamics. So starting with a family of quadratic polynomials on the complex plane, where the parameter C is also complex. Now we will define a full Julia set to be the set of all complex numbers where the iterations of that number or the orbit of that number stays bounded. And then I'll take the boundary of this set to be the Julia set. I'll call it Julia set. And then the Mandelbrot set is defined to be all parameters in C such that the Julia set is connected. So here you can see the set of all parameters, which is the Mandelbrot set. And for each parameter here, there is a nice picture, which is a nice Julia set for that. Also, I will define a polynomial on the complex plane is going to be set to be a post-critically finite map if the forward orbit of every critical point is finite. And now we can define the Hubbard tree. So a Hubbard tree of F is going to be a forward-invariant subset of the full Julia set that contains the critical orbit. It encodes also the combinatorics of F, so it's nice to work with. And the question here, which Hubbard trees I can construct pseudo-Anosov or generalized pseudo-Anosov. So let me go over some things from geometric topology or geometric group theory. Of course, we know that the Nelson-Thurston classification showed that every orientation preserving homeomorphism up to isotopy is one of three. It's either periodic, reducible, like the dent twist, or pseudo-Anosov. Of course, pseudo-Anosov are really interesting objects, and they are defined to be that a homeomorphism on a closed surface on a surface is going to be called, let's start with pseudo-Anosov, if there exists two transverse foliation and a number lambda greater than 1, such that the homeomorphism stretches one foliation by a factor of lambda and compresses the other one by a factor of 1 over lambda. Now, lambda is called the dilatation. It's also the Lyapunov exponent. And the logarithm of this lambda is going to be actually the topological entropy of the map. And the transverse foliations are the stable and unstable foliations. Now, we can define generalized pseudo-Anosov to be a very much similar if we have still a pair of transverse foliation, but we need also a set sigma of finite numbers where we have on the surface, there will be infinite singularities that accumulate at the points in sigma, at finitely many of them. So again, generalized pseudo-Anosov, we are allowing infinite singularities to occur, but they need to accumulate at finitely many points. Now, the question, given quadratic polynomial, can we construct pseudo-Anosov homeomorphism? If F is a post-critically finite map on the tree, is there an extension of it on the surface such that the extension is a generalized pseudo-Anosov? Or can we find a continuous map from the pseudo-Anosov to the polynomial such that that it's semi-conjugate, so such that this commutes? Now, for the real quadratic polynomial, it's done by de Carvalho and Farber, and here I am expanding or generalizing it to the complex plane. So I look at the Hubbard tree, and I want to find which Hubbard trees that I can construct generalized pseudo-Anosov from. Now, my Hubbard trees that I want us to work with are going to be the non-degenerate Hubbard trees, which means that the critical point is in the middle that splits the tree into two parts. I'll call the upper branch and the lower branch, so BU and BL. So here you see the upper branch in red, the lower branch in blue, and I look at what happens to these branches under the map. So I look at the images, and I will fix the endpoints, and I will see if I can isotope these two images apart. In this case, of course, you can see that I can do that, and in this case, I will be calling this Hubbard tree a crossing-free Hubbard tree. If there is a crossing, then there's no such embedding. I'll say that there's a crossing, or T has a crossing. Example, this is a crossing-free Hubbard tree, whereas here a Hubbard tree with crossing. So you can see we cannot isotope these apart because of this part. So now, before going to the result, I just want to define what does it mean for the map F to be extendable to a generalized pseudo-Anosov map. So F, which is a post-critically finite map on the Hubbard tree, is going to be or set to be extended to or extendable to a generalized pseudo-Anosov homeomorphism if there exists a surface S and a generalized pseudo-Anosov, and such that this generalized pseudo-Anosov phi is an extension of F, which means that this diagram commutes. And then the main result, which says that if F is post-critically finite map or quadratic polynomial, and if T is a Hubbard tree, then F and T is extendable to a generalized pseudo-Anosov if and only if it is crossing free. Of course, the main direction of the theorem, like if I start with a tree, how to construct generalized pseudo-Anosov, I can show the proof with an example by construction. So I'll start with a tree, and very quickly here, I'll just show that starting with a tree, I will thicken the tree. The colored part are called junctions in between our sides, and then I'll define a thick map on the thick tree. It takes junctions to junctions and stretches and compresses the sides. There is a folding happening because of the critical junction. Then I will need to construct a train track. Of course, I'm not going over this construction. It's a bit long, so maybe another time, but let's say we have the train track. Now, with this train track, look at the sides. I will construct these rectangles and then glue them. And to construct these rectangles, we will need first to associate to the map on the train track a Markov matrix that for each entry it counts the number of times the image of one side crosses the another side. And then I will calculate the leading eigenvalue, which will be our dilatation or our Lipinov exponent. And the core entropy of F is going to be log of that lambda. And then I will use the dimensions of the coming from for these rectangles coming from the right and left eigenvectors. So I will build these, I'll glue them, and here also there is some explanation that I cannot spend time on, but maybe if you have a question, let me know. And then we will glue them, and we will have the quotient surface is going to be a homeomorphic to S2. So this is the main result. We are getting generalized pseudo-Anosov, and the core entropy is the same as the core entropy of the polynomial. And here I built these, and you can see if it closes, it is homeomorphic to the sphere. Thank you.